The road has been long. Through time, Paratech has worked tirelessly to always keep innovating and making the best tools to save lives. Now, on the cusp of a new era, we are entering the future of rescue. Before facing the future, you should know the past. Let's go back.
The real start to Paratech was the saw. Partners Robert Benker and Howard Leibovitz discovered the Swedish chainsaw that they thought would be effective for the fire service, and that proved to be correct. And that took off and all over the United States. It had to have special blades. Howie Leibovitz, he invented a negative pitch that nobody else could replicate, so we began making those ourselves. That's what gave us the manufacturing core to Paratech. We had this capability, and now we wanted to fulfill it with new products, new ideas.
It all started back in 1962. Our first ever tool was the Pry-Axe.
The Pry-Axe was developed by a battalion chief in New York City Fire Department. He had what he thought was a prototype for somebody to make it for him. This was while I was in the Army. My two partners, Howie and Bob, agreed that they'd like to try it. The first run was 2,000 units. When I got out of the Army in 1965, my first task was to get rid of these damn Pry-Axes because they're costing us a fortune sitting here. Little by little, they gained recognition, and we started building in improvements to the tool. And each time we made a release of forgings, we tried to incorporate features into the tool that would make it better. Every change in the tool was an improvement.
The tool that started it all. Over 50 years of continuous production and continuous improvements. World famous Pry-Axe. From one innovation to another, meet the hooligan tool.
The fire departments had very limited choices. Some fire departments were doing forcible entry with a crowbar that they got at the Ace Hardware store. So when they'd see this quick and decisive forcible entry tool, that was a fairly quick success, and we did send thousands of them.
We used to weld them, but the weld wasn't as good because it was damaging the structure of the material. So we pressed this.
The first three-piece production Halligan tool, and the first to improve upon the original Chief Halligan design.
I designed new claw and new head, so it's more practical. Claw is more sleek, but it's bent more, and it has a nail pulling feature. The head, it had two wings like on the side of the pike. When you hit it in a metal lead in a car, you could twist and you open up the hole, so it became a completely different tool.
And the hooligan tool has a major place now in fire departments.
Recognizing the need for new, innovative firefighting tools, the Beal tool.
Howie wanted to design this very small personal tool.
Spell it backwards, it's Leib.
Leibovitz. That's what he wanted, so I had to do that. He wanted to have a Beal tool, and that's the name. A few years ago, I redesigned that again. It's cast out of stainless. It's very strong, stronger than steel. It's like 180,000 psi. All we do is put a rubber handle on it. We just press it together, so this is like indestructible.
The smallest, most portable axe in a fireman's arsenal. Designed by Paratech's founder, Howard Leibovitz, to ensure that even officers have a tool they can carry without restricting personal mobility. Something completely new, the PRT.
The idea behind it, it's the economy of scale and it's safety, because up until that time, to get percussive force, you're swinging a sledgehammer and you take a backswing and it's dangerous. You're able to direct all the force. There's no deflection.
I wanted to make it lighter and more modern. I developed one with the aluminum housing, so it was lighter, it was more efficient, and there was a special lock that when you turn, you can lock it in different positions.
All of the force that is being expended is directed at the point of the tool.
The ultimate disaster preparedness tool. No strings attached. Safely direct optimum impact exactly where you want it. New problems require new tools. Titan Crash Axe. The lightest, most advanced personal rescue axe. Designed with and for the pararescuemen, the PJs, U.S. Air Force Special Operations Command.
This was the first product I worked on. Some members of the Air Force pararescue guys had purchased one of our Beal tools, and they had tested it without us knowing about it. And they said, hey, we really like this product. Here's the thing, we need the whole thing to be under 2.5 pounds, because everything that goes up in an airplane, the weight matters a lot. That's why I'd ever drive to titanium. We started that project with full-size pencil sketches to clay models, to 3D models, to I had a whole Tupperware container full of 3D prints of just tweaking things and changing things, and the whole thing is skeletonized, kind of trellised out so that provide a really strong grip with gloves and gets the whole thing under that 2.5 pound limit.
Engineered to be as light, strong, and customizable as possible. The only X of its kind. Having refined our manufacturing and engineering expertise, we move to revolutionize another plane of rescue. Our road continues. The future of rescue still awaits. Come along next time when we uncover how Paratech made a yellow X mean the safest rescue.
I went to work and I said, Howie, why did you hire me? And he said, because you're crazy. I like guns.
Hola a todos, bienvenidos a un nuevo webinar. Estuvimos ausentes alrededor de un mes, pero no estábamos de vacaciones, sino que estábamos preparando el webinar que vamos a ver ahora. Hace un mes terminamos en la parte introductoria de zanjas y la parte de travesaños, así que hoy vamos al nivel avanzado. Es probablemente uno de los webinars más interesantes que vamos a tener en nuestra serie, ya que tenemos dos invitados que son expertos en el tema y los referentes mundiales en lo que es rescate en zanjas. Probablemente muchos de ustedes no han visto nada de lo que ellos van a exponer hoy día. De hecho, vienen a botar ciertos mitos, ciertas creencias y ciertas técnicas que hemos utilizado hasta los últimos tiempos. Ellos son expertos de la User Training Foundation y son miembros de la Fuerza de Tarea número 1 de Michigan, y como les decía, son expertos con muchos años, con respaldo de ingeniería. Hay muchos ingenieros que trabajan detrás de esto, y por lo mismo este va a ser un webinar largo. Vamos a estar alrededor de 90 minutos aquí, pero vale la pena porque les aseguro que todo lo que van a ver no lo han visto nunca. Así que pongan mucha atención, traten de tomar un papel y un lápiz porque hay hartos datos interesantes. Como siempre, traten de escribir sus preguntas aquí en el chat del costado y las vamos a ir respondiendo en la medida que vayamos avanzando. Un poco de paciencia porque es largo, pero como les decía, no se van a arrepentir. Son conceptos nuevos en su mayoría para muchos de nosotros, y también para los que han hecho cursos en los últimos 5 años se van a dar cuenta que hay técnicas que ya quedan obsoletas y que hay un tema de seguridad importante que tenemos que ir abordando. Así que no los interrumpo más, vamos con este webinar.
Welcome, gang, to the Paratech Virtual Workshop on Trench Rescue. During this program, we'll be discussing soil and trench rescue shoring. At the conclusion of this workshop, you should be able to recognize basic soil mechanics identify trench rescue shoring principles and best practices, determine lateral soil forces at trench rescues, and utilize trench rescue shoring specific tabulated data in order to select the correct shoring materials and equipment. During this presentation, we'll be discussing many of the trench rescue shoring myths and folklores that have worked their way into the fire service industry. We'll encourage you to take notes and ask questions. I'd like to begin by acknowledging this distinguished group of professional engineers who have provided most of the information that we will be presenting today. We begin with Don Barrier, who's a professional engineer in Charlotte, North Carolina. He's the guy that put this program and committee together initially. He is a structural specialist for North Carolina's Urban Search and Rescue Task Force 3. Dr. Oliver Taylor, geotechnical engineer with the Research Division of the U.S. Army Corps of Engineers. Dr. Marie Labaugh, geotechnical engineer, works with Montgomery County. She is a structure specialist for FEMA's Maryland Task Force 1. Dr. Janos Gurgley, a structural geotechnical researcher for the University of North Carolina and a structure specialist for North Carolina Task Force 3. And Craig Dashner, professional engineer and construction manager, who is the structural specialist for Michigan's Task Force 1. My name is Ron Zawlocki. I'm an old fire dog with more than 45 years of hands-on experience in the fire and rescue profession. I'm the co-author of the book Trench Rescue and the manager of the Facebook page called Trench Rescue Shoring. I'm proud to be co-hosting this virtual workshop with my friend Craig Dashner. Craig is the structural specialist for Michigan's Urban Search and Rescue Task Force, and he is the co-author of the next edition of the book, Trench Rescue, that will be available in a few months from Jones and Bartlett Publishing. Craig will begin the presentation with soil mechanics. It's very important for you as a rescuer to understand soil mechanics in order to distinguish shoring principles that are used at trench rescue emergencies and distinguish those from the shoring principles that are used at construction sites. They are two different topics. It's unfortunate that a lot of trench rescue training programs are teaching trench construction safety principles while ignoring the conditions that we encounter at most of our trench rescue incidents. So with that, I'll give this to Craig. Craig, you're up to bat, my friend.
Thanks, Ron. So I'm going to be presenting on basic soil mechanics. There's been volumes and volumes of books that have been authored about soil mechanics over time with geotechnical engineers. But my goal here is to try to take those soil mechanics and get it down to something that first responders can understand, to help them understand why soil fails and collapses. So most first responders look at a trench like this and say, that trench wall looks solid. And that could be the furthest thing from the case. So if you consider the definition of a solid, I'm not going to read it all to you, but really the key portions of it are items that are able to maintain their shape and volume, are stable, structurally rigid, and resistant to forces. So if we consider this concrete wall with high compressive strength concrete and high tensile strength steel, it meets that definition. It's stable, it's volume stable, it's rigid, and it's resistant to forces. But now if we look at the soil is made up of many different particles arranged such that their shape and volume aren't stable. It's not rigid, and it's not resistant to forces. So soils really aren't a solid. And if you think a trench wall is solid, you're fooling yourself. So looking at this image, if you go out in nature and look, you never see vertical soil walls. You just don't see it. Now, somebody might dig and it holds a vertical wall for a while, but soil just does not have the strength to maintain a vertical wall. That's why you see things like concrete and steel, and sometimes those don't even stay stable for very long due to the forces that are behind it. So if you think of soil, soil is made up of individual particles. You've got these large sand particles, you've got mid-sized particles that are silt, and then you've got these tiny particles that are clay that can really only be seen individually under a microscope. And soil can be made up of any of these or even all of them. And it always has air around it too. So soil itself is not a solid. So if you look at a trench, when it fails into chunks of dirt that are falling off. It's not a complete wall that falls off and stays solid. It's something that breaks up into pieces and parts, and sometimes individual grains if it's dry enough. So where do the forces come from that act on a trench wall? The largest single force that you have to deal with is gravity. Now, I've included the image we had previously here with the soil structure. So if you can imagine gravity pulling down on all these individual grains over time, it's going to pack them in more and more so over time. And as it goes down, it starts wedging in between other particles, which creates a lateral force pushing outward. So that really causes the lateral force that we have to deal with when it comes to shoring trenches. It's that wedging force of particles from gravity that turns into a lateral force. Other external forces we deal with are surcharge loads. Now, most often it's the spoil pile that's set back on just behind the trench lip, but it can also be materials that are there. It can be equipment that's placed there. The other thing we have to be worried about too is vibrations. Vibrations can do a lot to destabilize the soil structure. And this could be equipment that's running on the site. It could be a nearby railroad or even a nearby highway. So it's always a good idea to get everything shut down within a pretty large radius of the trench site to keep those ground vibrations down. Water is another problem we have to deal with all the time too. Many trenches are being dug in order to deal with some type of a water issue, whether it's installing sewers, water mains, fixing broken pipes. There's always water present. And water being in a trench can change the characteristics of the soils that we have that we're dealing with. So what water does to us is it creates hydrostatic pressure. Like I said before, the grains of soil are all separated. There's these little tiny air spaces between them. And when you saturate it with water, that water pushes in every direction, up, down, and out the sides. And when you get a lot of water in there, it starts increasing that lateral pressure by pushing it out sideways. So if we watch this little video here by Professor John Berlin, he'll demonstrate the effect that water has on soils. So in this first one, he pulls out a dry soil, and you can see how it just pours out into a mound. Now in the second cup here is the same exact soil, but with some water added to it. And you can see how it maintains its shape and size coming out of the cup. Now the third one is identical to the second one, same amount of water in it. And again, he pulls it out and you get the same column. It self-supports. But now watch what happens is he adds some water to the base of the plate. So just that little bit of additional water caused this thing to fail instantly. So what happened there is, like I said, the water started filling up that grain space in between sands and pushing it apart. And once the base destabilized, the whole thing came collapsing down. So why do some trenches stand for long periods of time while others collapse? It's a pretty easy answer. Some soils have more internal strength, and some trenches have more loads that are acting on them. So if you look at the right side of the screen, it's actually a video playing. It takes a while to develop here, but you do see a shallow trench that was dug, and there's a pretty large crack in it. And if you keep your eyes on the crack, you'll see it consistently getting wider and wider and wider. So basically what's happening is you've got a force in that soil that's trying to collapse that trench, and the soil strength is not enough to keep it from collapsing. And the result is the trench collapses. So what is internal strength in soil? Basically, it's made of three different mechanisms. So you get soil friction, adhesion, and cohesion. And I'll explain each of these as we go forward. So internal strength, soil friction. Basically what this is the particles all have some shape and angularity to them. And as these individual grains start locking into each other, that creates a soil friction. Again, if we look at the picture on the left, that is the soil when it was poured out of the cup. And if you did that over and over and over again, you're going to get this pretty much the same shape of the mound there due to the soil friction of the particles. So like I've mentioned before, the individual particles of soil, you've got anything from angular particles all the way to well-rounded. And if you imagine trying to stack BBs, you just can't do it because there's no friction between them. No matter how much you try to stack them, they always go down to the lowest thing, so you're down to one layer. So the same thing can happen with soil when you have well-rounded particles. Now your angular particles, there's more lips and edges that are going to lock into the other ones that will give you a higher soil friction. The other thing that plays a big part of it too is the compaction of the soil. The more air you have between those individual soil particles, the more they can move around as you put loads on them. They can twist and they can kind of wedge in, which will push other ones sideways. Whereas where you get compacted soil, there's not many places for it to move. It's all been packed together already. So a compacted soil is going to give you a much higher soil friction capacity than a loose soil would. The second mechanism we're going to talk about is adhesion. What adhesion is, and it happens primarily in sandy soils, is if you add a little bit of water to it, just like we saw in that video, you can go from just having a pile to something that will hold its shape. The reason this happens is the water coats those individual particles, and once they're coated with water, they attract to each other. So it's kind of almost like a magnetic force that holds it together. So if you have just enough, it will hold together. But again, if you put too much, that water starts pushing those particles apart and will lead to collapse, just like we saw in the third cup on the video. And our final mechanism is cohesion. This only occurs in clay soil, and it's an attraction that happens at the molecular level. You have positives and negatives that are in those molecules, and they attract to each other. Now, again, clay is the only soil that has that molecular attraction. So in summary, as we just went through, all soils have elements which provide internal strength, which influence the stability and probability of collapse. So this internal strength comes from the soil friction, comes from adhesion, and it comes from cohesion. Now you can have any one of those or all three of them acting to give you your total internal strength of the soil. And then the opposing side of that is the external forces. So the external forces come from the lateral load that just happens due to gravity, surcharged loads that are up on the trench lip, vibrations that can be anywhere near you, and then water and its impact on soil. So like I said previously, if you have more external forces that are trying to collapse the trench than you do internal forces that are trying to resist that collapse, then that leaves you in a position where you're going to have a trench collapse. So that concludes my section here, and I will hand it over to Ron for the next section.
The basic knowledge of soil mechanics that Craig presented are meant to provide an understanding of why shoring principles and practices used for stable and static soil conditions may not be applicable to the unstable and dynamic soil conditions so often found at trench rescue incidents. Workers who install and repair underground utilities are typically on the scene during the excavation process. That fact provides an opportunity for shoring trenches before the soil becomes active. Rescuers, on the other hand, typically arrive at the scene after a collapse and during a time when the soil is unstable and dynamic or moving. Statistically, more than 75% of trench rescue emergency incidents involve unstable and dynamic soil conditions. Shoring that might be appropriate for stable rock and certain static and stable soil conditions may be entirely inadequate for the soil conditions found at your trench rescue incident. Post-collapse conditions, like the one in this photo, are clear indicators of soil with weak internal strength. Unstable and dynamic or moving soil breaks apart and fails when it's not adequately supported and retained. The retention and support of moving soil particles requires 4 fundamental shoring principles. Those 4 principles are: collect the load, transfer the load, distribute the load, and resist the load. These principles and practices can be found in the U.S. Army Corps of Engineers shoring guidance for structural collapse incidents. They've been safely and effectively used by urban search and rescue teams for about 2 decades. Fundamental engineering construction for buildings includes the same principles. They include things like columns, beams. In this case, a large beam is called a girder, which holds other smaller beams. In this case, floor joists are called beams, and those hold the decking or sheeting up above those that keep the moving materials from falling in between the beams. Pretty much the same concepts go on here in structural collapse shoring. The beams are up here. We call them headers and sole plates. We have posts or struts. Very, very much the same concepts that we need to put into place during trench rescue shoring. With trench rescue shoring, we simply take that same construction and tip it 90 degrees or on its side. And instead of resisting forces that are coming down, we resist forces that are horizontal or pushing sideways, like in a trench wall. Shoring principles, collect the load. Very important that we utilize this principle in order to keep our small particles of soil collected together. Okay. Trench rescue panels of laminated Arctic birch and engineered strongbacks in what you'll learn in section 4 to be a composite construction are very strong, and they'll collect and retain those lateral soil forces that are associated with most trench emergency incidents. Also, to collect the load in collapsed walls that have voids in them, we must fill the voids in order to maintain soil contact and prevent movement behind the panels. Backfill, commonly used, include installing airbags, soil from the spoil pile, timbers, backshores behind the panels, and covering the void areas. So the backfill should cover at least 80% of that void area, which is caused by the collapsed section of wall. Transferring the load from a soil wall to a point of suitable resistance. So how do we take and the moving part of the wall and transfer that load to resist and keep it from moving? It's called transfer the load, and we do that with struts. The best practice for struts are struts that are readily adjustable in lengths, have measurable activation forces, and can be installed and removed without entering the trench. Those are the best practices for unstable and dynamic soil conditions. Both Paratech gray struts and the longshores, or what we call the gold struts, are capable of rapid adjustments from air pressure. We can expand the length of the strut very quickly and easily. The pneumatic controllers and gauges provide measurable activation forces. And most importantly is the fact that both Paratech gray and gold struts can be installed and removed without entering the trench. There's a lot of confusion over the topic of strut pressures and forces. And we'd like to try to help eliminate some of that confusion. To begin with, we need to understand there are two distinct forces associated with the use of struts. One force is called the strut activation force. All struts used for trench rescue shoring have a mechanism that creates an activation force. With timber struts, we typically use opposing wedges or screw jacks to tighten up the struts and create that strut activation force. With hydraulic and pneumatic struts, they use cylinders and compressed fluid or air to create those activation forces. That strut activation force in these pneumatic struts is a result of the area, which is found at the end, how many square inches are at the end of the strut's piston. And we have a diameter on the gray struts of 2.5 inches in that area and 3 inches on the gold struts. And the formula for that is the radius squared, and remember that the radius is half of what the diameter is. So in this case, on the 3-inch strut, the radius would be 1.5 inches. Radius times radius times pi, or 3.1. We'll give you a minute to, a couple of seconds to write that down if you want to write down that formula. Pi times radius squared will give you the surface area of that circle that's found at the end of the piston on the struts. The best practice for activation forces in collapsing and unstable soil conditions is to get an activation force of between 1,000 and 1,250 pounds. With the gray strut, the 2.5-inch diameter, using our formula, we get a surface area of almost 5 inches. So an example of how to use that formula is we have 200, if we set our gauge at 200 pounds per square inch, and we have 5 square inches, we multiply 200 times 5, and that gives us an activation force of about 1,000 pounds. If we up that to 250 pounds, still times the 5 square inches, we get 1,250. And with the gold struts, because it is a bigger diameter, our strut pressures, pounds per square inch, are less, but we're still trying to get very close to that best practice activation force of 1,000 to 1,250 pounds. The activation force is important. It pushes the panels and wales tight up against the wall. So we want enough pressure and force for that to happen. And two, the activation force of the struts can actually make the panels and the wales stronger and give them more capacity. So we don't want too much pressure, but we don't want too little pressure. And in these types of soil conditions, 1,000 to 1,250 pounds is what we're shooting for. This is how we get there. In this video, you will see that the activation forces of this strut they ended up being less than 1,000 pounds of force, somewhere around 500 pounds of force, created a total failure of the shoring system. Now, this was not a failure of the strut. This was a failure of the design, which was put together or dreamed up by a firefighter and never was reviewed or designed by a professional engineer. And those are the kinds of myths and folklores. This thrust block system, the original thrust block system, was never engineered or tested. And it is a dangerous system. If you're using that system, I would urge you to stop doing that and to find another alternative for your L-shaped trenches. Write this down. This is a pretty good, simple rule to remember. If the shoring system you're setting up cannot resist the recommended strut activation forces, it in no way will it be possible for that system to resist the forces of dynamic soil pushing against it. It just can't happen. So if your system is moving when you put the strut pressure to it off of your air gauge, you have a poorly designed system, and you better get something else in place. The other force that's associated with struts is created by this dynamic and moving soil force. For example, if we were to take this 4x4 section outlined in red, section of panel, that is collecting the force and the load behind that panel. And if, let's say, we take an arbitrary force of 14,000 pounds, which soil forces can easily create, and it pushes against this panel, the panel and strongback push against this 3-inch diameter gold strut, it transfers that load to the wall on the right side here. And it is transferring 14,000 pounds of force through a very concentrated or small 3-inch diameter that has a 7 square inch base at the end of that. So that is what's called the thrust pressure. The thrust pressure is really what we need to be concerned about being able to resist. The activation force puts our strut into place. We have to be prepared for the thrust pressure or thrust force that the soil can create. Again, those myths and folklores that have entered into our shoring system, this thrust block system just does not work. The next principle is, after we've collected the load and transferred the load, we need to get it across the trench and distribute that load over a larger area than the strut base size. So struts transfer the load to a point of resistance in a very concentrated manner. That concentrated load placed on the trench wall with weak and unstable conditions can actually cause rather than prevent collapse. So the best practice for taking that load and distributing the load coming through the strut is to take the strut base and place a strong and stiff trench rescue panel behind, in between the strut base and the wall. And that helps take that force of the thrust and distributes it against, in this case, a 4x4 section of panel rather than a 5 or 7 inch strut, the end of the strut piston. Last very important part of the shoring principles is to resist the load. Voids that are behind the panels must be filled to add strength and stability and resistance to the panel. The point of distribution must be strong enough to resist the thrust pressure being transferred through the strut. The way we resist the load, we showed earlier this airbag in place to help collect the load from the force of the soil coming from left to right. But we also need to have that resistance or backfill in place to strengthen and help resist the force that's coming from this trench wall moving from right to left. So we need to fill that in, and again, backfill should cover at least 80% of that void area. So for shoring dynamic soil conditions, the unstable conditions, the collapsing conditions that we see at most of our trench rescues, these are important points. Collect the load, transfer the load, distribute the load, and resist the load. There are other types of shoring that has different types of principles. Basically, the types of shoring that are done in underground construction work, where right as the trench is being dug, shoring can start before the soil loses its internal strength and starts to move. One of those principles is something called skip shoring. Skip shoring is a simple form of support. It's usually used in stable rock, very stiff clays, and other stable and static soil conditions. And these conditions must be self-supporting, and they must be capable of generating something called soil arcing. Soil arcing is an observed phenomena that really began to be seen with the use of soldier piling and lagging. They begin to notice that there was some arcing taking place, and the soil was attracted to these points of resistance, being these vertical pilings. And in between, there was much less soil force being pushed out against the lagging. So the manufacturers of hydraulic shores came up with the idea and tried it and are successful in certain types of soil conditions by creating vertical points of resistance by using uprights, vertical strong uprights, and struts. They can try to replicate the types of resistance that's occurring in these soldier piling, and these are the arcs that are created in some types of soil. This is how this would look. The distance in between these has to be determined by a qualified person on the scene before the shoring takes place. I asked our group of structural engineers how they felt about using that skip shoring idea at trench rescues. Dr. Marie Labaud did a study and actually wrote her dissertation for her doctorate degree on that particular subject. And what she says is that in dynamic soil conditions, without the use of sheeting in between your struts, there's an unaccounted for force right at the face of the trench in between the struts. And in the real world applications of trench rescue, that exposed face is likely to blow out and cause the trench wall to collapse. A skip shoring, the manufacturers of hydraulic shores put together this skip shoring where they have these rails, these vertical rails, and struts going down the rails to create those points of resistance. But they also came up with something called a spot shore, and spot shores were made to use in conjunction with these vertical shores. And the spot shores were made to supplement or to be used with the skip shoring in places where there's obstructions like pipes utilities crossing the trench where that vertical upright just wouldn't fit. So we can use the two of these together. It was the original use of spot shores. Firefighters have attempted to stretch that envelope and want to use this thing called spot shoring without panels and without those vertical struts or uprights. That, again, is not designed or supported by any structural engineer. And I asked our group of experts on this if they would use spot shoring during trench rescue incidents, and all of them said no. I also checked with the rescue manufacturers of struts, the leading manufacturers of rescue struts in North America, Paratech, ProSpan, Rescue Tech, and Hearst Airshore now is no longer selling them, but they're still out there. I asked them if they would endorse or support the use of spot shores in collapsed conditions, and every one of them said emphatically no. Dr. Taylor tells us that the use of skip shoring or spot shoring is only valid for an extremely limited number of soil conditions. And in those soil conditions, the soil properties and behavior characteristics have to be known. And he says that such conditions and knowledge of soil properties and characteristics are essentially never encountered at a trench rescue situation. So can somebody go out there and determine those soil characteristics and mechanics? Yeah, somebody like a geotechnical engineer using soil boring samples and laboratory type testing could do that pretty accurately. The chances of you and I going out there and accurately making that soil analysis are slim to none. And Slim just left town. It's just not going to happen. It would be a crapshoot. This is my poster child for reasons that we shouldn't be using field soil analysis to make any determination of how to shore a trench. This is a very qualified person with quite a number of years of experience working for a large city in North America. She determined that this soil was stable, had an equivalency to an OSHA type A soil reading condition, and she entered the trench, and shortly after that, this soil that she thought was stable was unstable and collapsed and could have killed her. It pinned her. The local fire department arrived and knew this lady and asked her what the soil conditions were. They went ahead and she told them still type A soil equivalent. And they went ahead and used this thing called spot shoring. They kind of did their own version of spot shoring. It was trying to expedite the rescue. They took high risks by using this particular shoring principle in this type of soil. Would not recommend it. Now, firefighters, I can tell you after 45, 46 years of working with firefighters, they will stretch the envelope. So if you tell them that spot shoring has to be placed every foot apart, they'll stretch the envelope and end up doing something like they did on this actual rescue scene. Can be very shaky. The fact that they did something makes and it worked and it didn't collapse, makes firefighters want to think that it's okay, that it's proven. Let me tell you about this one. This is my Orange X shore. I have set this Orange X shore up on a variety of different soil conditions across the United States 73 times. Just paint an X on that. During those 73 times of shoring with my Orange X, the soil never collapsed. The trench wall never collapsed. So the fact that you did something doesn't mean that it's good, and it doesn't mean that it's safe. You might have just been lucky. And as Chief Brunacini told us years ago, good luck can make you dumb because it makes you think that you're smart. And that's what I'm afraid of with this idea called spot shoring. So soil arcing principles for skip shoring and spot shoring, they work in some soil conditions, uncommon soil conditions for us responding to trench rescue. And they do not work in unstable and collapsing soil conditions. So section summary, most trench emergency incidents result from the collapse of unstable and dynamic soils. Shoring principles and practices required for unstable and dynamic soil conditions are different than those that may be required for things like stable rock or some Class A, very stable clay conditions. The best practice for rescuers is to use premium shoring equipment to always collect the load, transfer the load, and distribute and resist the load. You won't go wrong if you use that principle. You may be in deep trouble if you use other principles that are not based for those types of soil conditions that we encounter at trench rescues. In section 3, we'll learn about a new method that was designed for first responders to rapidly and accurately determine worst-case lateral soil forces. It's important for us to know lateral soil forces so that we can select the shoring equipment and materials that'll both protect us and get us in the trench quickly. It's time to pull out your notepad and pencil and put on your thinking cap. Civil engineers have several theories and formulas to help them determine lateral soil forces for different types of soil. This drawing shows a variety of soil pressure diagrams, which are part of the process. The diagrams represent a number of geometric shapes that soil can exert forces on. They include rectangular, triangular, trapezoidal, and other shapes which are dependent on the soil properties and mechanics. Unfortunately, all of those soil pressure diagrams require soil analysis equipment, expertise, and experience that first responders just don't possess. So a big problem exists in that first responders do not have a way to rapidly and accurately determine those lateral soil forces that are going to have an effect on your trench rescue shoring system. In 2018, Dr. Oliver Taylor and Dr. Marie Labaugh, at the request of the Army Corps of Engineers and FEMA structure specialists, designed a method for first responders to rapidly and accurately determine lateral forces at the scene of a trench emergency. The methods have been published in an international civil engineering journal and have been reviewed and vetted by structural specialists from the FEMA, SUSAR, and U.S. Army Corps of Engineers Urban Search and Rescue Group. The beauty of this method is that it does not require technical equipment, expertise, or even a lot of experience. The TL method requires just a tape measure to determine the lateral soil forces and a method for using the specific tabulated data for trench rescue shoring. The base of the TL method uses the soil failures present at a trench rescue incident to determine the lateral soil forces and to predict future soil failures. Dr. Taylor tells us that the answers to the questions are right there at the trench. Unlike the methods used by engineers that determine soil forces based on soil properties and mechanics and soil pressure diagrams, the TL method uses the size of the largest failure present to determine the lateral soil force that will push against your shoring system. The area outlined in red represents a 4 foot by 4 foot section of panel, or essentially a half panel. The white section behind the 4 by 4 sections of panels represent 16 square feet of worst case soil. Each section behind that represents an additional 16 cubic feet of soil. The TL method allows us to accurately predict the maximum soil forces that could be exerted on each 4 by 4 section of your shoring system. The resultant used in TL method is based on 16 cubic feet, creating 1,100 pounds of lateral force against your shoring system. Since the formula uses 16 square feet or a half panel as a constant, we simply need to add one more dimension to that to change square feet into cubic feet. And that dimension is the distance from the trench wall back to the farthest point of failure. In the photo on the left here, that's about a 1 foot span. So 16 feet of panel in front of this section, going back 1 foot, we would have 16 cubic feet of soil pushing sideways against your system. The fissure or crack or the breaking point of this soil on the right is larger than that. It is 3 feet back from the wall. So that one would represent 3 times the amount of the soil pressures on the left. So 3 times 16 or 48 cubic feet of soil, 3 times 1,100. This one would be pushing on each 4 by 4 section of panel with 3,300 pounds of force. Let's take a look at 3 definitions that we'll be referring to throughout this section. One is something that we call the simple L, SL, and it is the distance that we just looked at, the distance measured in feet from the furthest extent of failure back to the trench face. And we just showed you a simple L of 1 and a simple L of 3 in the previous slide. There's something that's called a surcharged L, and that is the amount measured in feet, and we're always going to round up to the next foot. If you have something that's 2 feet 8 inches, we're going to call it 3 feet. So always round up to the next foot. The amount measured in feet of the surcharge load that is within that simple L distance. And then finally, this thing that we call the total L is the simple L plus the surcharge if a surcharge exists. In other words, if an object, a heavy object, is within the distance of the simple L, then a surcharge exists. Let's take a look at this thing called the simple L. It is the distance in feet measured to the farthest failure extent that's perpendicular or at a 90 degrees to the excavation face. So here we have three failures in this particular trench. The one down here at the bottom is a slough-in type failure, and that goes back about 2 feet from the original trench wall or face. There's another one above that that's a little bit less than 2 feet. And then there's the farthest extent of failure at 4 feet, and that is a pretty deep and big fissure. So in this one, we've got 3 different measurements, but the thing that we're going to use as a simple L is the 4 foot, and we would call that a simple L of 4. Well, what are common failure points? What are the things we're supposed to be looking for? Dr. Taylor tells us that the answers are there. Here's the things we want to be looking at. The distance from the original wall back to lip shear. Usually those are just a couple of feet. Lip shears are usually not a big simple L, but we need to measure that. If that is the farthest point of failure, we're going to use that as our simple L. Other types of collapses would be that slough-in. So an estimation, you can get a tape measure up at the top of this thing without standing on over the top of your slough-in and estimate the number of feet from the original face to the very farthest point of failure in the slough-in. Another thing would be deep and significant fissures or cracks, and this one here that I'm pointing to would probably result in a pretty good sized wall shear. But until it shears off, we are just going to count this particular fissure. And when is a fissure, when does a crack become significant? Well, there can be a bunch of small cracks on the surface on the lip of your trench that result from drying out. Especially clays tend to dry out and get these superficial cracks and fissures. But whenever a crack is more than 1 foot deep or more than a ½ inch wide, we're going to count that as a failure point. Spoil piles. Take a look at the spoil piles, and what we're concerned about is finding that SL, that simple L, the furthest point of failure that is at the trench, and then determining how much of this surcharge, in this case the spoil pile, is within that 5 feet. Now, if there was a crack or a fissure here, you wouldn't see it because the pile has covered it up. So I just superimpose that 5 foot mark. So you could see in this case, because the spoil pile is all the way to the trench wall, there are 5 feet. There are all 5 feet of that simple L distance is covered with this object, with this spoil pile, and that is the surcharge. So we would use the amount of surcharge as the number 5, as well as the simple L, 5. Take a second, get your notepad out, write down these 4 things. Simple L, the area of the surcharge within the SL, the simple L. Additional load from the surcharge, which is going to come from a chart that we're going to learn to read in just a minute. And then number 4 would be, how much do you add to the simple L to get the total L? How much surcharge do you add to the simple L to get the total L? Copy that down, and you're going to be using that a few times during this section. Here is the surcharge calculator chart. Take a look at that. We have 2 columns on the left that have to do with a surcharge that's a spoil pile. And then there's a blank column that separates the 2 columns on the right that have to do with equipment. And we're going to come back and discuss equipment and what that is and how to use that side of the chart in just a couple of slides. So for right now, we have this spoil pile, and then we have this how much to add. So the number under the spoil is how many feet of the spoil is over the area that we're calling the simple L. And in our last case, that was 5. So we would circle this 5, and then the row on the next to that, on the right-hand side of that, tells us the additional load we need to L to add to that simple L of 5. So here's how this one would work. Simple L of 5, there are 5 feet covered by the spoil pile. Go down to the 5 from this number, it tells you what to add. Okay, and this is how your worksheet would look. Simple L is 5. The area of surcharge within the simple L is also 5. Going to our chart, it told us that we need to add 3 to the simple L. Add the simple L, which is 5, to the surcharge L, which is 3, and your total L becomes an 8. Try this one on your own. This is going to be your problem to solve. Simple L is 7. The spoil pile now sits back 4 feet. So there's not a complete spoil pile across your 7 simple L. It's less than the 7, right? 4 less than. So see if you can fill in those 4 key points on your worksheet based on this chart. And this is what your worksheet should look like based on a simple L of 7. There are now 4 feet of that 7 that don't have a spoil on it, leaving 3 feet of surcharge within our affected simple L area. So it should look like this. The simple L is 7. How many feet of that spoil power within that 7? There's only 3. How much do you add from your chart? When you went down to the 3, it told you to add a 1. And in this case, we add the 7 to the 1 and come up with a total L of 8. Surcharge for heavy equipment. Measure that simple L, the point, whatever it is. I'm making it real simple on these. A lot of times you're going to have multiple points of failure, and you're going to take the one that is farthest away from the trench wall. So to make it simple, this one we have a simple L of 5, and then see if any of this machine is sitting within 5 feet of the trench wall. This sits back 4 feet, so that would leave 1 foot of this machine that we're going to be worried about. Okay, 1 foot. Then we're going to take a look at the equipment side of the surcharge chart, and then add them together to come up with the total L. So again, 5 feet is the simple L. There's 1 foot, and we're going to go all the way over here to the right to the number 1. There's 1 foot of equipment that is within that simple L. And then go to the column next to that, and it tells us how much more to add. Now, remember, each time we add a 1, we're adding an additional 1,100 pounds to that 4 by 4 foot section of panel. If we've got a 3, right, if we need to add the number 3, that would be adding an additional 3,300 pounds to that panel and the strut holding the panel. So in this case, it would just add a 1, and we would add the 1 to the 5, and we come up with our 6. So try this one on your own. The simple L is 7. The machine is sitting back 3 feet from the wall, and you need to determine how much machine is left within the 7 feet of the simple L. Fill out your worksheet, the 4 points on your worksheet, and see if you can come up with the correct total L, because the total L is what we're going to use in the next section, section 4, to select the proper strut, the proper panel, and the proper whale. Here's what that worksheet should look like. The simple L was 7. There was 3 feet of that not in the 7, right? It's set back 3 feet. So that gave us the area within the 7 was 4. And then when we looked at our chart, next to the 4, it said add 5, because it's equipment. Equipment is going to be always heavier than the spoil pile, so that you get a larger number to add. And then we would add the 7 to the 5 and come up with a total L of 12. Now, equipment, we're going to consider things like a dump truck, a front end loader, an excavator, a backhoe, heavy steel or concrete pipes that are sitting on the lip of your trench in your rescue area, right? And if they're sitting back farther than the distance that the simple L is, farther back than what your failure has occurred, we're not going to count that. We don't have to worry about that. According to our engineers, the point of farthest failure is going to be, we can predict that things will happen within that point of farthest failure within the next 12 hours. So if you can't execute a rescue in 12 hours, you probably won't be worried about doing this type of calculation. You probably ought to start out by retraining your whole trench team, right? If it's taking you more than 12 hours to get a guy out of a trench. So 12 hours, that farthest point of failure is going to be the maximum. That's going to be the maximum. I mean, absent something like a 747 landing on your trench lip and parking right over your rescue area, there's nothing significant enough that's going to happen that's going to make that worse than that. So now what happens when there's no failure? This has never happened to me before. Every one of the many trenches that I've gone to for body recoveries and rescues have always been a result of a collapse or soil failure. But in the event, maybe less than 25% of the time, you come to a trench that hasn't collapsed or hasn't shown any point of failure. You have to figure out a way to determine how you're going to shore this thing. And there's a depth conversion, a depth to simple L conversion chart that we have here on the right. So what do we do? Instead of measuring to the simple L, because there is none, we're going to measure the depth of the trench. And then we're going to come over to the depth conversion chart. And anything under 4 feet, you're probably not going to shore anyway. But 4 to 8, I've lumped them all together and said the equivalent simple L for something 4 to 8 feet is going to use a 6. Simple L is 6. And then each foot after that down to 20 gets its own designation. So in this case, 14-foot deep trench, we follow the column down on the left to the 14, go across, and it tells us that that has a simple L equivalent of a 10, simple L 10. Okay, on this one, this example, we have a depth of 10 and no failure, right? But we also have a spoil pile. So we need to take a look at our depth conversion chart and see what's the equivalent conversion of a 10-foot deep trench. What is my simple L? And then I can figure out how much of that spoil pile sits within that simple L. So we had 10. We come down the depth conversion chart to 10 over to the top, and it tells us that the simple L is 7. Back from this slide, I know that the spoil pile set back 2 feet. If the concerned area goes back 7 feet, that means that 5 feet of that spoil is within my simple L. So I go to the spoil pile side down to the 5 and come across, and it tells me that I would add 3 or 3,300 additional pounds of lateral force to the system. So simple L of 7, 5 feet of that are within the simple L. That tells us to add 3. 3 plus 7 is 10. Do this one on your own. This is an 11-foot deep trench. Jot that down. And then I'm gonna move over to your charts for you. And the spoil pile sits back 4 feet. Use your depth conversion to figure out what simple L 11-foot deep trench gives you, and then determine how much spoil pile is within that converted simple L. And write those 4 numbers down on your worksheet. And your worksheet should look like this. The converted simple L was an 8. 11, right? Simple L was an 8. The area in feet within that simple L was 4, because that machine set back 4 feet. So there was 4 feet left within the 8. And it tells us on our surcharge load to add 2. So we take the simple L, converted simple L of 8, add 2, and we have a total L of 10. And that's how we do the depth conversion. Now, all of these charts that we've been showing you up on the screen here are going to be available with a link. We're going to provide you with an operations level shoring ops guide that will have those charts in them. And you can print that up in the form of a little pocket guide and carry that with you if you choose to use the TL method and our TL method tabulated data. So the section summary, you should know how to find that simple L with your tape measure. You should know how to add a surcharge from a spoil pile to determine a total L. You should know how to use the chart to determine the surcharge load for equipment. You should know how to convert depth to simple L. And finally, you should be able to add surcharge to a converted simple L. Just be able to do all of those things. If there are things in here or in this summary that aren't sinking in, make sure that you include those in your questions and submit those questions so we can go back and resolve the things that people are having problems with. So, okay, you can do this thing now, the TL method, you can determine the soil, lateral soil forces, so what? What is that going to do for you? Okay, well, here's the deal. The total L is the rapid and accurate estimation of the lateral soil forces in worst case trench rescue soil conditions. If you can figure out the worst case trench rescue soil conditions and set up a proper selection of shoring equipment to safely, but not over shoring to take too much time, but to safely get in there quickly, and you use that same method for all trenches that you come to, it's going to be quick and it's going to be safe, okay? A group of professional engineers have developed tabulated data for rescuers for these worst case conditions. And that tabulated data will tell you what shoring equipment is safe to use based on this thing called the total L. And in the next section, in section 4, Craig Dashner will show you how to use the tabulated data once you can determine the total L. Craig, you got section 4, buddy.
Okay, thanks, Ron. So now we're going to go over tabulated data. What you see in front of you is a chart that Paratech has that they have in their literature for their struts. It was stamped by a professional engineer. Essentially, this chart was developed by taking tested capacities of Paratech struts at different lengths and using soil pressure to come up with a spacing for struts, either in a horizontal or vertical direction. Now, charts like this have been part of tabulated data for a long time, but they haven't been especially useful to the rescue industry. And you can understand that primarily by looking at the horizontal spacing. The horizontal spacing, you have spacings of struts anywhere from 2 feet up to 8 feet. And I think most of you know that our rescue panels that we use are basically 4 foot by 8 foot sheets of plywood. And if we use those in a vertical orientation, struts are just naturally going to be spaced every 4 foot horizontally. And then vertically, they can be adjusted to fit. And it's for this reason that rescuers primarily haven't used this tabulated data, because it just doesn't work for their situations. So the tabulated data that we're going to present to you here is presented for worst case dynamic soil conditions. And as Ron showed in the TL method, it uses clues on scene that you can get to know what kind of soil pressures you get. Now, if you look at the video that's playing on the screen, you've got a trench that looks pretty solid. You don't see any signs of issues down there. I mean, obviously, you've got a worker down there working in an onshore trench condition, and then all of a sudden, wham, it falls on them. If you looked very closely, you could see one little piece of dirt raveling that hit the pipe, but other than that, there was no warning before this went. Now, it could very easily have another collapse the exact same way with rescuers in there. So that's why it's important to have shoring in, and you can support those type of soil conditions. So the 3 charts of tabulated data that I'm going to share with you today are for Paratech struts, for whales, and for trench rescue panels. Now, when we put these charts together, everything was put together for a 2-to-1 factor of safety. And to make sure that there's, call it that margin of error in there, in case the soils, if you get a little water in there, the soil pressure might be a little higher than what we're predicting with the TL method. That gives a little room for error. So these should work for for most common trench rescue sites. Now, the important thing to remember with these data charts is that they're intended for short-term rescues. And when we say short-term, we're talking about a shift, say 12 hours. Now, would 13 hours be breaking the rules on it? Not really, but you shouldn't be using this in a rescue that's lasting for, multiple days on end. As soil sits longer, the forces start to increase more and more. In the TL method, soil pressures were developed on this shorter term span. These charts also use published capacities for manufactured equipment. So there is nothing that was done to the Paratech chart. We didn't go back and recalculate capacities for the struts. We used Paratech's published capacities for a 2-to-1 factor of safety in comparison to the soil pressures coming out of the TL method. Anything using wood, as you'll see in the whale charts and the trench rescue panel charts, basically used published capacities from recognized national lumber standards that many engineers use, and bending strengths that are provided by the manufacturers. And we've also done destructive testing on many of these things to make sure that the assumptions we're making are accurate and come up with viable numbers. So we'll start with the strut chart. A few things I want you to look at right off the top: maximum vertical spacing with 4 foot horizontal. So basically this chart is made to have struts every 4 foot horizontally. So if you're using your standard 4x8 rescue panel with a strong back up the middle, you'll have struts at every strong back, which gives you that 4 foot spacing. And the only thing that's going to vary on this is your vertical spacing in between struts. Now, when we look down a little further, we see we have 2 columns for gray struts, and then we have 4 columns for gold struts. So this is showing both options. The next line down, you'll see trench width. So trench width, less than 8 feet for gray struts, widths from 8 to 10 feet for gray struts. And then for gold struts, you have less than 10, less than 12, less than 14, and less than 16. So by measuring your trench width and going to the next higher column, that's going to tell you vertical spacing you want. So I'm going to run through a scenario coming through here, and you're going to want a pen and paper. Excuse me. So here's a checklist, and if you could write this down on a piece of paper and kind of treat it like like you're making a table. So write these words down on the left side and have rooms for columns down on the right side, because we'll be using this a couple times as we go through these scenarios. So you're going to want to have trench width, simple L distance, area of surcharge within the simple L, additional load from the surcharge, whether it be spoiler equipment, total L, and shoring equipment selection. So this is basically going to be the result of all the things above. So hopefully you've got that all written down. Like I said, if you can do it like a chart where you have 2 or 3 columns to the right, then that'll save you having to write this down again. So here we have our first example for strut use. And struts are a little bit unique just because in the length of strut has an impact on its capacity. So we'll always need to know what the trench widths are for selecting which struts we're going to use and what spacing we're going to have them at, because a wide trench, you're going to have lower capacity out of your struts than you would a narrow trench. So one of the first things we always do is to measure the width of the trench. Now this sketch here is showing us some information, and it has the trench width shown here at 4 feet. After that, we have to determine what the simple L is. So we're going back to Ron's presentation on what that is. We know what signs of damage at the trench and trench lip. So our image here is showing us a 3 foot belly failure that collapsed into the trench. But then we also have fissures going out to 4'6". Now, as Ron told us, this is the next sign of failure. So even though this did fail at 3 feet, our next sign is 4'6". So that is really what our simple L is. And then we want to round that up to the nearest foot just to keep things easy. So this would have a simple L of 5 feet. And we also have a spoil pile up here, and it's 2 foot back from the toe. So again, if our simple L is 5 feet and our spoil pile is 2 foot away, 5 foot would be back here. That means 3 feet of that spoil pile, 5 foot minus 2 foot, is within our simple L. So this is what we have on the checklist so far. So your trench width is 4 feet, your simple L is 5 feet, and the area of surcharge within the simple L is 3 feet. Again, that was the 5 foot simple L minus the 2 foot back from the soil. So that'd be a 3 foot area of soil that's in the simple L. So now we're going to look at our surcharge table that we have to determine how much we have to add to the simple L to get the total L. So again, with the simple L of 5, and we have 3 feet of soil within the simple L, that tells us we have to add 1 foot to the simple L. So if we take our 5 foot simple L plus the 1, that gives us 6 feet. So in this case, our total L for this trench would be 6 feet. So this is what our chart looks like now. So using that surcharge chart, we knew to add 1 for this, which gave us a total L of 6 feet. So now we have to go and select our struts. So here's the Paratech strut table that I showed before. So basically now we know L equals 6, so we can enter our table here at L equals 6, and then we have to go to the right until we find a column, that will work with a 4-foot strut. So obviously 4 foot's fairly narrow. The first row, or the first column, which is a width of 8 feet, will work. So with an L of 6, a trench width of 4 feet, we can use gray struts at a 4-foot spacing, 4-foot vertical spacing. Now, it's also good to keep in mind that if you only have gold struts available, that the gold struts will work too. L equals 6, gold struts less than 10 feet would work at a 4-foot spacing. Now, I don't know the struts in and out as well as Z does, but I'm not sure if you can get gold struts at a 4-foot length that would allow you to use them that. So from a chart standpoint, either of them will work, but if you don't have, if you can't get the gold struts that short, then you'd be, only at a gray strut for that. So this is what we end up with our checklist. Now, all of this we had filled in previously using the total L of 6 feet in the table. That tells us we have gray or gold struts with 4-foot vertical or 4-foot horizontal spacing. So basically 2 struts per panel. So here's a scenario that I'll let you guys work through yourselves as I talk. So basically the same type of thing. We've got an image here that's showing us a trench. So again, we follow the same process. Measure the trench width. So we look at our chart here, or image here, and it's got information for us. So this will tell you what the trench width is. Next, we determine the simple L. And again, this trench has a 3-foot undercut type failure that fell into the trench, but it also has some fissures present that are at 6 feet. So by looking at those, you know what your simple L is. Then our next step is to determine the additional load from the surcharge. So what we have here is we have a spoil pile that is 3 feet back from the lip. So the amount of spoil pile within the simple L is the simple L minus the 3 feet here. And there's no equipment present that we can see, so there doesn't appear to be any equipment surcharge. So we have to take all that information and determine the total L of this trench. So here we are again. We still have the same picture up, but now we've got the surcharge chart for you. So again, if you know what your simple L is, and you know where your spoil pile is, if you subtract those 2 numbers, then you go to the spoil side here. And if you have a certain amount of spoil within the simple L, it tells you what to add to get the total L. So then with that, if we flip back here real quick, if we had an L of 6 feet, a simple L, and we added 1 to get to the total L, that's an L of 7. If we go to our strut chart and take L equals 7, and we have to remember our trench width shown was 15 feet. So we have to go across till we find something that works with 15. Now this is 14, still a little short, so we have to go to the last column here to get 3 feet. So that will give us a vertical spacing of 3 feet for a 15-foot wide trench at L equals 7. So this is the checklist all filled out. Now, hopefully you were able to do this with the hints I was giving you, but you should have came up with a trench width of 15 feet, a simple L of 6 feet, area of surcharge within the simple L of 3 feet. That was 6 feet minus 3 feet pushed back from the toe. And using the chart, that should have given you an additional load from the surcharge from spoils of 1 feet for a total L of 7 feet. And then going into the strut chart, that tells you that you have to use a gold strut with 3-foot vertical spacing, 4-foot horizontal spacing. So this is what your result should have been. So now we'll discuss the whales. This is the chart we have for whales. And again, you'll notice up top says 4-foot maximum vertical spacing. The other important thing to notice here is distributed load. Now, by using a distributed load as opposed to a point load, you can almost double the capacity. There's actually, you can almost quadruple it. But, so those are two important things to keep in mind. Now, we have an 8-foot span, which means 8 foot between struts that are supporting the whale, or a 12-foot span. So basically, an 8-foot span, you'd have one panel being supported by the whale, and the other two panels on either side have struts on them. In a 12-foot span, you'd have two panels supported by the whales. And we've got whale types. So we have common materials that teams are using for whales. So you have 6x6 lumber, 8x8 lumber. Both of those would be either Doug fir or spruce pine fir. Hopefully they'd be top quality lumber without a lot of knots or checks or splits in them. We have 7-inch by 7-inch LVL beams or Paratech aluminum whales. So I want to talk a little bit more about distributed load to make sure you understand it. So on the left with our image, if you've got a standard rescue panel layout where you are using a whale to support this center panel, if you don't have any spacers and it's just the strong back touching the whale here, that is going to take all the soil force behind this panel and apply it to the whale at this point here. And that's called a point load. And basically that has the highest effect on the strength of the beam. Now, this top one here is showing the use of spacers. So what happens with these spacers is it takes up the gap between the plywood of the panel and the whale. So as the load starts to develop behind these panels and push on them, the plywood will usually start to bend a little. Well, the plywood contacts the spacers and puts the load directly into the whale. So now it's being loaded along a majority of its length. And when that load gets spread out like that, it has the result of increasing the capacity of that whale to support loads. Now, it's very important to point out that those spacers must also be at the end of the beams too. Now, that helps to prevent the beam from bending at the ends, which has a tremendous impact on strength. On the right here, this is what these spacers look like. Basically, they can be 2x8s or 2x10s that are nailed together in an L-shaped fashion, and they just get dropped in between the whale and the panel, in between the strong backs. So here's our whale use checklist, and this is going to work exactly like the strut use checklist. So the things we need to do to determine what whales to use: we have to know the span between the struts on the whales. We need to know what the simple L is. We need to know the area of surcharge within the simple L, the additional load that comes from that surcharge, whether it's spoiler equipment, and again, that goes back to the surcharge chart we've used, which will give us our total L. And then by knowing the span and the total L, then we can do our selection of shoring equipment from our whale table. So here's a scenario for whale use. In this case, we've got a trench, and again, it doesn't matter how wide it is now because the width has zero effect on the ability of the whale to carry the load. So we have a failure here, and that depth is shown at 5 feet. And we don't see anything else around here. We don't see any fissures or anything like that indicated. So this would tell us that our simple L is 5 feet. No spoil pile here. On the other side, we do have equipment, but that equipment is set back 7 feet from the lip of the trench. So as we know from our table here, whether we're doing spoil or equipment, we're looking for the amount of that that's within the simple L. Since the simple L is 5, none of that equipment is within this simple L here. Now we need to know our span. So if we laid out our trench rescue shoring to go over that failure, basically we can have 3 panels wide. The middle panel will not have a support. So that's telling us we have an 8-foot span. We have 8 foot from the strut supporting this panel to the next strut, which is supporting this panel. So now our checklist looks like this. We know we have an 8-foot span. Our simple L is 5. Our area of surcharge, which would have been the equipment within the simple L, is 0 because it was further away than the simple L. So that does not add anything to our total L, and we have a total L of 5. So now we're going to go into our whale table to select our equipment. So the way this chart works is now we have to go in and look at these entries to find out for an L of 5 what will work. So at an 8-foot span, we're right here, a 6x6 will not work because it doesn't have a capacity great enough. An 8x8 will work. It does have an L of equals 5, but then also a 7x7 LVL or a Paratech aluminum whale will work for that. So that gives you 3 different options. And remember, it has to be distributed, which means you need spacers in between the strong backs and past the end of the last strong back. So this is our final solution for it. So again, the information we had previously, and going into the table, the equipment that'll work is an 8x8 Doug fir, spruce pine fir whale, a 7x7 LVL with laminated veneer lumber, or a Paratech aluminum whale. So that brings us to panels. I would assume everybody is familiar with rescue panels. What has typically been used throughout the years has been fin form with a 2x12 lumber strong back bolted to it in 3 places. What we found, and it was something that I brought to Ron many years ago, and we've done a lot of testing on, was composite construction. Now that's how this table is broken up. On the right, you will see values for capacity for non-composite construction, and on the left, you'll see ones for composite construction. And you'll see that the composite construction values are much, much greater. Now, what composite construction is, and the best way to explain it is to think of a steel I-beam that gets welded together. So you can take 3 plates and you put them together in an I-shape and you weld them to each other. That weld is stronger than the material themselves. And basically what it does is takes those 3 pieces of steel and turns it into 1 new piece of steel. So we're considering doing the same thing with wood. So instead of just bolting the strong back to the wood, that allows the wood, the lumber, and the panel to move relative to each other. There's slip between them. So when you connect them with bolts, they're just acting as each individual beams. But when you connect them together with construction adhesive, which is most appropriate for wood, and keep them from slipping relative to each other, that now they're acting as a new, larger, solid piece of wood that acts together. And by doing that, we get a much greater capacity out of it. Now, we'll provide a link that shows you how to build these panels compositely, and more importantly, test them to assure that the way you're building them is getting you that composite behavior, because it sure wouldn't be good to expect an L of 20 and really be getting an L of 5. But, if you take the time to build them right, you can get nearly 4 times the capacity out of them just by adding construction adhesive. So now we're going to walk through the panel use checklist, so we can determine what panels we need for a trench incident. So again, this should be very familiar to you because it's very, very similar to the other ones. But what we're going to need is our simple L, our area of surcharge within the simple L, additional load that comes from that surcharge, whether it be spoiler equipment. That way we can find the total L, and then finally go into our chart and select the shoring equipment we're going to use. So here's our scenario for selecting panels. Again, we have a trench shown here. The width doesn't matter because that doesn't impact the trench panels. We've got a fissure here shown 7 feet back from the trench lip. So again, we know that's our simple L now, right? We're getting good at finding that. Our equipment is 5 feet off the lip. So we know that 2 feet of that equipment, 7 minus 5, is within the simple L. So this time in our surcharge chart, we're going to look at the equipment column. We go down to 2 feet, and that tells us to add 2 to the simple L. So now we're going to find the panel that we can use. Now going back, our simple L was 7 feet, and we added 2 for the equipment, so that gives us a total L of 9 feet. So So now what we do is we go in here, and you'll notice at L equals 9, none of these non-composite panel options will work. If we come over here, only our composite ones will work. So either you can use a 2x12 LVL with thin form, which would give you a capacity of L equals 20 feet, or a 2x12 sawn lumber strong back with thin form, which would give you an L of 11 feet. A panel with just CDX plywood is not going to work for this case. So here's our final solution. Simple L of 7, area surcharge within the SL is 2, which adds 2 to our simple L, giving us a total L of 9. And here are the two solutions that we said would work, both of these being composite panels, which means they're screwed and glued. So as a summary, the tabulated data that we gave you in the charts is designed for use for trench rescue soil conditions. Again, all of our horizontal spacing was set for a maximum of 4-foot spacing. So basically it will line up with the strong backs on adjacent panels. And this is designed using the T-L method to include unstable and dynamic soils. So we went through how to use the Paratech strut charts. We gave you the simple checklist to use to be able to select the proper struts. We did the same thing for whales and talked about distributed loads for the whales and how important that is. And then we went through the panel charts to help you select what panels you're going to have. Now, the one thing I hope you get out of all of this, if you study the whale charts and the panel charts, is if you look at premium lumber like LVLs and fin forms, how much more capacity you get out of them if you take the time to build them right and to get the premium materials. So that wraps up my section. I'll hand it back over to Ron for the closing.
All right, gang. So this is the workshop summary. During this virtual workshop, we discussed basic soil mechanics. We identified trench rescue shoring principles and some best practices. We determined and provided you with a quick and rapid and pretty simple tape measure and book equipment way of determining lateral soil forces at rescue incidents. And finally, we showed you a way to utilize trench rescue shoring specific tabulated data to help you select the proper and safe shoring materials and equipment. If you have some notes down or want to make some notes based on that summary on any of the topics that we've discussed here, we are going to move on to the question and answer period. And we'll be entertaining your questions here in the next couple of minutes.
Bien, llegamos al final de este webinar. Muchas gracias por conectarse hoy. Esperamos que les haya gustado. Fue un gran esfuerzo tener a Craig y a Ron aquí exponiendo para nosotros, pero creemos que son los mejores exponentes en el mundo hoy día respecto a lo que es rescate en zanjas. Espero que haya sido novedad, porque para muchos de nosotros esto es nuevo. Los que ya tenemos cursos con más de 5 años, esto es totalmente nuevo. Como dijo Ron, por ahí se desarrolló el método T-L el 2018, así que probablemente ya lo vamos a empezar a ver en los cursos, en los siguientes cursos, ya cuando el tema pandemia termine y podamos volver a la práctica. Estudien, no traten de hacer esto sin práctica y sin los equipos adecuados. Acuérdense que el rescate técnico requiere 3 piezas fundamentales: personas, preparación y equipos. No solamente la buena voluntad. La buena voluntad nos puede llevar a accidentes. Pero esperamos que les haya gustado. Cualquier duda la pueden seguir aquí escribiendo en el chat, porque va a quedar abierto unos minutos. Y desde ya los invitamos a seguir con la serie de webinars. Si viene algo ya de rescate vehicular avanzado, vamos a tener invitados importantes también los mejores exponentes del mundo en lo que es extricación y estabilización pesada. Así que muchas gracias y nos vemos en el próximo webinar. Joe, please.
The road has been long. Through time, Paratech has worked tirelessly to always keep innovating and making the best tools to save lives. Now, on the cusp of a new era. We are entering the future of rescue. Before facing the future, you should know the past. Let's go back.
The real start to Paratech was the saw. Partners Robert Banker and Howard Leibovitz discovered the Swedish chainsaw that they thought would be effective for the fire service, and that proved to be correct. And that took off, and all over the United States, it had to have special blades. Howie Leibovitz, he invented a negative pitch that nobody else could replicate, so we began making those ourselves. That's what gave us the manufacturing core to Paratech. We had this capability, and now we wanted to fulfill it with new products, new ideas.
It all started back in 1962. Our first ever tool was the Pry-Axe.
The Pry-Axe was developed by a battalion chief in New York City Fire Department. He had what he thought was a prototype for somebody to make it for him. This was while I was in the Army. My two partners, Howie and Bob, agreed that they'd like to try it. The first run was 2,000 units. When I got out of the Army in 1965, my first task was to get rid of these damn Pry-Axes because they're costing us a fortune sitting here. Little by little, they gained recognition, and we started building in improvements to the tool. And each time we made a release of forgings, we tried to incorporate features into the tool that would make it better. Every change in the tool was an improvement.
The tool that started it all. Over 50 years of continuous production and continuous improvements. World famous Pry-Axe. From one innovation to another, meet the hooligan tool.
The fire departments had very limited choices. Some fire departments were doing forcible entry with a crowbar that they got at the Ace Hardware store. So when they'd see this quick and decisive forcible entry tool, that was a fairly quick success, and we did send thousands of them.
We used to weld them, but the weld wasn't as good because it was damaging the structure of the material. So we pressed this.
The first three-piece production Halligan tool, and the first to improve upon the original Chief Halligan design.
I designed new claw and new head, so it's more practical. Claw is more sleek, but it's bent more, and it has a nail pulling feature. The head, it had two wings like on the side of the pike. When you hit it in a metal lead in a car, you could twist and you open up the hole, so it became a completely different tool.
And the hooligan tool has a major place now in fire departments.
Recognizing the need for new, innovative firefighting tools, the Beal tool.
Howie wanted to design this very small personal tool.
Spell it backwards, it's Leib.
Leibovitz. That's what he wanted, so I had to do that. He wanted to have a Beal tool, and that's the name. A few years ago, I redesigned that again. It's cast out of stainless. It's very strong, stronger than steel. It's like 180,000 psi. All we do is put a rubber handle on it. We just press it together, so this is like indestructible.
The smallest, most portable axe in a fireman's arsenal. Designed by Paratech's founder, Howard Leibovitz, to ensure that even officers have a tool they can carry without restricting personal mobility. Something completely new, the PRT.
The idea behind it, it's the economy of scale and it's safety, because up until that time, to get percussive force, you're swinging a sledgehammer and you take a backswing and it's dangerous. You're able to direct all the force. There's no deflection.
I wanted to make it lighter and more modern. I developed one with the aluminum housing, so it was lighter, it was more efficient, and there was a special lock that when you turn, you can lock it in a different positions.
All of the force that is being expended is directed at the point of the tool.
The ultimate disaster preparedness tool. No strings attached. Safely direct optimum impact exactly where you want it. New problems require new tools. Titan Crash Axe. The lightest, most advanced personal rescue axe. Designed with and for the pararescuemen, the PJs, U.S. Air Force Special Operations Command.
This was the first product I worked on. Some members of the Air Force pararescue guys had purchased one of our Beal tools, and they had tested it without us knowing about it. And they said, hey, we really like this product. Here's the thing, we need the whole thing to be under 2.5 pounds, because everything that goes up in an airplane, the weight matters a lot. That's why I'd ever drive to titanium. We started that project with full-size pencil sketches to clay models, to 3D models, I had a whole Tupperware container full of 3D prints of just tweaking things and changing things, and the whole thing is skeletonized, kind of trellised out so that it provide a really strong grip with gloves and gets the whole thing under that 2.5 pound limit.
Engineered to be as light, strong, and customizable as possible. The only X of its kind. Having refined our manufacturing and engineering expertise, we move to revolutionize another plane of rescue. Our road continues. The future of rescue still awaits. Come along next time when we uncover how Paratech made a yellow X mean the safest rescue.
I went to work and I said, Howie, why did you hire me? And he said, because you're crazy. I like guns.
The road has been long. Through time, Paratech has worked tirelessly to always keep innovating and making the best tools to save lives. Now, on the cusp of a new era, we are entering the future of rescue. Before facing the future, you should know the past. Let's go back.
The real start to Paratech was the saw. Partners Robert Banker and Howard Leibovitz discovered the Swedish chainsaw that they thought would be effective for